magnetic field due to solenoidal fields. Here consider a solenoid RS of length L. From the axis, let A be the radius of the solenoid. P is the point very well inside the solenoid. Okay. Now here let I be the current flowing in the solenoid. If N, capital N, is the number of turns in solenoid, then number of turns per unit length of solenoid will be equal to N. That is N equal to N by L. Now we have to find the magnetic field at a point P very well inside the solenoid. Okay. So here we come across three cases. One is the field at inside point, other is the field at axial end point, other is the field at center point of the solenoid. So let us consider the first case, field at inside point of solenoid. For that we have to divide the solenoid into narrow equidistant parts. Okay, we divided the solenoid into narrow equidistant coils. So we are considering one such coil AB of a width dx, which is at a distance x from point P. Now let us join P to A and P to B. Let PA is equal to R and triangle PAC. Here we are dropping a perpendicular from A on PB line, that is AC. Now angle PAC is d theta and PAO is theta. Okay. So now the same thing separately we draw here for case 1, field at inside point of solenoid. Now we know that magnetic field induction due to circular coil is mu naught N I A square by 2A square plus x square whole to the power of 3 by 2 Weber per meter square. Here in place of N we can substitute N into L. Now here we are taking the magnetic field due to current flowing in element of width dx. So in place of L we are substituting dx. So totally in place of N we substitute N dx. So now the equation becomes the field at point due to elementary coil of width dx is equal to mu naught N dx IA square by 2A square plus x square whole to the power of 3 by 2. Take it as equation 1. Now see from figure. Now if we consider the triangle PAC, sin d theta will be equal to opposite side AC, hypotenuse PA, that is AC by PA, which is nothing but AC by R. Okay. So from this AC can be written as R sin d theta. But d theta is very small angle. So d theta, it is taken approximately equal to d. Sin d theta is taken approximately equal to d theta. So we can write AC as R d theta. Right. Now next. Again now we are taking this triangle ABC. See here angle is theta. So here also angle will be equal to theta. So from this sin theta becomes AC by AB. Okay. Sin theta becomes AC by AB. That is equal to AC already we calculated as R d theta, and AB is nothing but width of element, that is dx. So from this dx is equal to R d theta by sin theta. Keep it as equation 2. Now again from the figure if we see, if we consider this triangle, we get R square will be equal to A square plus x square. Now substituting all these values in the equation 1, we will get mu naught N I A square by 2R cube R d theta by sin theta. So that is equal to mu naught N I A square d theta by 2R square sin theta. or mu naught Ni d theta by 2 sin theta. Here we wrote it as a by r whole square. Now again, if we go for the diagram, now we are considering this triangle PBD. Here is the angle. Now sin theta becomes opposite side is BD, that is A, and hypotenuse is PB. Okay. Now here see, AB is of very small width, so we can approximate PB equivalent to that of PA. So in place of PB, we can substitute R. So now sin theta becomes A by R. Now substituting this value here, we get mu naught Ni d theta by 2 sin theta, sin square, here whole square is there, sin square theta. One sin, here sin strikes off. It becomes mu naught Ni sin theta d theta by 2. Now this is the magnetic field at point P due to current I flowing through the element AB of width dx. Now we want magnetic field due to entire solenoid. For that, let us join P to R and P to S. Now PS is making an angle theta 1 with the axis, and PR is making an angle theta 2 with the axis. Okay. Now this theta 1 and theta 2 are the semi-vertical angles subtended by P by the first and last turns of the solenoid. So now the limits become theta 1 to theta 2. So now the magnetic field due to whole solenoid, magnetic field due to whole solenoid at point P, now it becomes integral theta 1 to theta 2 mu naught Ni sin theta d theta by 2. Now integration of sin theta is minus cos theta. So B equal to mu naught Ni by 2 minus cos theta, theta 1 to theta 2. Substituting the limits, mu naught Ni by 2 minus cos theta 2 plus cos theta 1, minus minus becomes plus. Now or B equal to mu naught Ni by 2 cos theta 1 minus cos theta 2. Now this is the general equation. Now the first case we are saying that when point is very well inside the solenoid, when point lies on axis of solenoid very well inside the solenoid, then theta 1 becomes 0 degrees and theta 2 becomes pi. Okay, theta 2 becomes pi, that is 180 degrees. Substituting the values, B equal to mu naught Ni by 2 cos 0 minus cos pi, that is equal to mu naught Ni by 2, 1 minus of minus 1, 2 strikes off. So now the equation becomes B equal to mu naught Ni is the required equation, Weber per meter square. In place of N you can substitute capital N by L, that is number of turns per unit length. So mu naught Ni by L, Weber per meter square is the required equation for the at the point inside the solenoid.